So thank you everyone for showing up to the Social Science Data Lab today. The Social Science Data Lab is an event series that provides a platform for tools and methods for the collection, management, and analysis and visualization of data in social sciences. It's jointly organized by myself, as well as my colleagues Dennis Cohn, who's here today as well, and Julian Bernauer, with the support of our research assistant, Nick Baumann. And today we have the pleasure to have Lisa Lechner here, who is assistant professor in political science methodology at the University of Innsbruck. And she will talk today about the inferential network analysis and big data challenges and opportunities. So before we get started and before I leave the floor to you, Lisa, just a couple of logistics. As I've already said before, you may ask questions during the talk or in the Q&A. Or after the talk during the Q&A by raising your hand in the Zoom chat. There's a function for that. Please wait for us to call on you, and then you can unmute your microphone and speak, or you can post your questions in the chat and we will read them out loud, or you can send us your questions by a direct message and we will then read them out loud. So just a quick disclaimer before we get started. We're recording this live stream and we'll post the recording on our YouTube channel. So that means if your camera is on or if you ask any questions, all of that will be recorded. But we can add something to that to hide your faces. So Lisa, the floor is yours if you want.
Thank you. Yeah, it is a pleasure to have this talk here. So I'm gonna share my presentation now. I hope you can see it all. First of all, a big thank you to the organizers of this workshop. It is a great pleasure to put my thoughts together on this topic. So today I'm going to give a brief overview of what inferential network analysis can offer us and talk a bit more about how we could potentially combine this with big data or larger data sets and networks. So first of all, the first section will be much about the motivation of networks and why should we really care about networks and why should we estimate networks or why not. So there are several gains and some sacrifices that we have to consider thinking about network analysis. The first gain, and I'm going to go into depth with regard to the gains, is that we have a much more honest perspective because let's face it, how many relationships in political science, in sociology, are really bilateral? And is it not better to really model what we see, like these multilateral relationships, etc.? The second thing is that network analysis offers us a way to calculate and calibrate better measures. And the third one is, and I will show you this, is that we have often a lower type 1 error using network analysis than if we use a poorly dyadic approach. But this is no free lunch at all. I'm 100% convinced by what network analysis can offer us and that it is a great challenge for us theoretically, but also methodologically, and that we can advance all of our fields in political science. Yet, first of all, we have to define very, very precise models. So our theory has to be rather precise and good in order to make the models work. Otherwise, it does not even converge. So in contrast to what we do in regression analysis, where we simply put in all these standard control variables, this will not be possible for network analysis. And that can be quite annoying. In addition, it is also a bit hard to think about structural terms. So what network terms really matter for our theory, for our analysis. And since this discipline is so young, this is especially a challenging part. We also need not only time to develop a good theory, but also right now for the estimation. So I would say, yeah, it's a young discipline, so this might be an excuse, but also we still lack a lot of efficiency in the estimation process. So it takes quite long to really estimate models with real data. So we need either a lot of computational power or some good ideas on how to recalibrate our models, our networks, etc. And this is the part that motivates me, especially to put down this talk and to think about it. How can we solve this issue that we have this great chance of having much more data, big data, to our hands, but we somehow fail to put it in network analysis because this estimation processes require so much computational power. And I have several of my own projects where I really got frustrated with this topic. So thanks again for the organizers, because it allowed me to invest a lot of time in reading what we could do and how we could improve our estimation with regard to bigger data and bigger networks. So let me move through the gains. I'm working in international relations, and there, of course, we have a lot of international agreements. There we more often have multilateral contexts than bilateral contexts. So just to show you an example here, what you can see here are the flags of countries that are member states of this comprehensive trade agreement, the follow-up of TPP, that the US exited. And you can see all of these countries collected here. In total, we have 11. And in a dyadic approach, we would have the thing that you can see on the left here. So we would have a relation, a tie between each individual dyad in the data set. That means that has two consequences. First of all, it does not really illustrate the structure that we have in this relationship. So it does not capture any power relationships, nothing in terms of this multilateral context. And in addition, the second point is that we have one observation several times in the data set, of course. Because, for instance, here we would have Australia with Japan, Australia with Canada, and then Canada with Japan, etc. So you would have this data imputation or this multiplication of data points, which, if you don't appropriately control for it, which is possible in a regression analysis, but nevertheless, it increases your certainty of the estimates. That means that you are much more certain of finding or rejecting the null hypothesis, but in fact, it might be wrong, and that might be due to the imputation or the multiplication of the data points. Of course, you can control for this point, so that can not be regarded as the main disadvantage of a dyadic approach, but it is something to consider. What I want to emphasize more on this slide is that why actually we don't illustrate a relationship that we have as it is. Why do we use this dyadic approach, but rather it is a network approach? And that is even more evident if you look at full networks. So what you can see here are all trade agreements between all the countries in the world. So we have 192 countries here. These are the nodes, the red dots here, and the gray lines, the edges, are the preferential trade agreements. So if you would think of this structure in a dyadic structure, you would miss a lot of this other information. So for instance, here you see that the European Union members are really at the center. So these are the old members here on the left, and these are the rather new members on the right. So you can see that the European Union is very central. This information would be disregarded in the dyadic approach. Or where is the US located, etc. So this information we can capture much better, of course, in networks. And it allows us to develop new and exciting theories on these structural elements. And the second aspect why networks are a really cool thing to do is because we can also generate better measures. So what I want to point here to is that in a dyadic relationship, we have actor A and B and their relationship between them. But we don't know the relationship that actor A has in mind or has as a backup. But if we're looking at networks, we really can model what are the backup options of each of the individual nodes. So if you're thinking about bargaining theory, for instance, there's this very prominent concept of BATNA, the best alternative to the negotiated agreement. So what are the alternatives to a current discussion that we have in the bilateral context? Or if you think about power, of course, like two states or two actors, their power is not only determined by their difference in GDP, for instance, but it's much more about their other options that they have outside. So what relations do they have to other states, etc. And this is a very, again, from my own research, where I find this really useful is, for instance, with regard to trade. So here, if you're looking at trade dependence, for instance, what we classically do is we use the trade share. So how much does the US, this is the prominent one, US trade to China and China trades to the US. But what we ignore with this measure is how many other alternative trade partners does China have and does the US have. So how does the trade diversification look like? And that crucially determines the power or the trade dependence between these two countries. So I would argue that looking at these alternative options that we have in this network directly modeled can help us to much better capture what's really happening between a diet. So these are the first two advantages, and the third one that I want to point to is that it has been shown that we see a lower type 1 error for certain variables that are correlated with either exogenous network terms or endogenous network terms. So what are these? Exogenous network terms, there we could think of, for instance, about a higher level degree. That means that if you have two actors, you look at how much joint relations do they have. So how similar does their structure in the network look like? So what you can see are two figures here where they estimated the bias that they would have in a conflict network. So what they did, they simulated the conflict network in order to know the true relations, the simulated relations, where they included correlations between variables and exogenous network variables. So these are precisely the things that I just mentioned, like these higher degree variables, where you consider the similarity in a network structure of two nodes. And they also included correlations between covariates and endogenous network terms. So these would be things like how high is the tendency of clustering, how high is the tendency of forming two paths, etc. So these are different network structures. And with this model, they used the exponential random graph model, which I'm gonna talk a bit more later in the talk. They used a classic network model, a classic inferential network model, and also created network terms that they included in a logit model. So in a classic logit model, they created these network measures and included it as a coefficient, as a variable. And when you look at the left side of the figure, you can see the type 1 error rate for those variables that correlate highly with these exogenous network variables. So that these variables we were able to control for in the logit. And the green line and the blue line with the cross are these logit models, and the black one is the full model. So what you can see here is that, first of all, the logit, where we did not control at all, or they did not control at all for these exogenous network variables, has a much, much higher type 1 error. So the hypothesis, this null hypothesis, is much more often rejected than what we should have done. And if we include these exogenous network terms, then suddenly this type 1 error rate drops, and we agree in terms of the logit and the network model. So if if you think that your theory is biased probably by variables that are exogenous network terms, you could even include this in your regression model and be fine. But you will not be fine if you have correlated structural terms. So that means that if there are, for instance, if the clustering influences your, or is correlated with a covariate that you have in the model. Let's say, for instance, the clustering dynamic really correlates with the regime type that you measure for each node in terms of explaining the conflict. So if you have this problem, then it is really hard to estimate a good model avoiding inferential network analysis. So here you can see that the black line here, the full exponential random graph model, really has the lowest type 1 error. Whereas both logic models, even though if we control for network variables, we can only control for exogenous network variables, of course, these are in both scenarios higher. So the conclusion of this is that if you have bias, omitted variable bias in terms of endogenous structural terms, then you're better off estimating an inferential network. Okay. So with this in mind, knowing that it might be quite expensive in terms of time and computational power, but there are quite some gains that we can have from network analysis, I want to give a quick navigation through network tools and focus particularly, first of all, on inferential network analysis, but most importantly, on exponential random graph models, because these seem to be really explosive in the sphere of network analysis. Okay, so one basic distinction that I want to make right at the beginning is that we can have descriptive network analysis and inferential network analysis. You're all aware of this, and yeah, slowly inferential network analysis comes into the literature. So right now we have quite a few papers using inferential network analysis, but until very recently, most papers that I've read on network analysis really used simply descriptive analysis, and were able to publish this in quite high-stake journals, which I was sometimes surprised, because what we are interested in is making predictions in social science. So I think it's valuable, of course, to do descriptive network analysis, but I think the exciting thing for us really is in this inferential part. And another distinction that is quite important conceptually is, what do we want to model? Do we want to model the complete network, or do we want to look at one particular node? Do we want to look at the egocentric network? So these are some basic distinctions that we have to keep in mind. And since inferential network analysis seems to be the exciting part where we can really push the field forward, I want to give a quick overview on this. So basically, for the very simple approach, so let's say we have no time or no panel, but simply one time observed network, we have several options. Of course, time I will discuss later, dynamic models. But let's start with the one in the middle, because this is not really a model, I would say. This is simply a parametric test looking at how similar and different are matrices, and using some significance levels that you can then implement in other models. So this is not really a full-fledged model, but it elaborates one of these first thoughts in inferential network analysis. What is quite often discussed and used is the latent space approach. And this is an approach where we think of triangles in the network. So what we assume here is that, let's say, Cosima has a connection with Dennis, and Dennis has a connection with me, then we would predict that Cosima and I also have a connection. So this is an assumption that this latent space approach uses in order to plot the points in this latent space. So it just assumes that the dots in there are connected once they share a node. So this is the assumption, and with this in mind, they can model these dependencies. These dependencies, however, land as a control in the error term, so it will not be possible for us to interpret these substantially, these endogenous structures. So the control for it, so you have unbiased results, but it's hard to interpret. And it is also quite tricky to model it. And then the last one are exponential random graph models, which there is a lot of development going on, and that's one reason, but also the quite easy implementation of it. I would like to focus on this and talk a bit more about the core idea and what we can do. But at this point, I also like to say that latent space approaches should not be disregarded, because for some situations where we have very tricky networks, it can be a solution for us. So instead of estimating an ERGM, an exponential random graph model, latent space approaches can help us to get out of this loophole of degeneracy where the exponential random graph model just doesn't converge. So yeah, this is a model that we should definitely keep in mind. And this is a brief overview of the advantages and disadvantages, but basically I mentioned most of them already. So let me walk you through the basic idea of this very classical model that most people use nowadays, estimating inferential network analysis. It is called ERGM in short, and it really starts from the idea that we have to think differently about the data generating process. So if we are thinking about a regression analysis, we would look at the univariate distribution, and from this distribution we would draw the observations, and then we can estimate how we can then find our parameters that estimate our y. But in the network approach, we have a different problem set, because we suddenly drop this very, very central assumption that we have in regression analysis, which is the independence of observations. We can no longer accept this, of course, because this is the core idea of network analysis. So how can we get over this and consider this interdependence between nodes? So what they came up with is thinking about the data generating process coming from a multivariate distribution. So instead of this univariate distribution, we suddenly draw not multiple observations, but one single network from this multidimensional distribution. And that allows us to have one single observation, one network, because suddenly we don't have, like in a regression analysis, the different observations, but one simple observation, which is the network. And from this, we can estimate the parameters. So there is a different thinking process right at the start. So we don't start from the univariate distribution, but rather from this multidimensional space where we draw the network from. So this is just that already the data generation process is thought from a different angle. But what is really important then is how can we make the link? So we have this single network that we want to observe. Network analysis, especially these ERGMs, have as a dependent variable, as a dependent matrix, only one observation, only one network. So we have to think about a way how we can get parameters to explain this one observation. How can you get variation in there? Okay, so we have this one single network, and then we need to find parameters that explain this one single observation. So we need to get in some variation. How can we do this? So what we do is we take the nodes as fixed. So the amount of nodes that you have in a network is fixed. Let's say, because I started with this example, of trade agreements. You have all countries in the world, so you would have 192 nodes, and that would be the number that would be fixed. And then you would use a stochastic process in order to create a lot of different networks. So basically the aim would be to create all possible networks that these 192 nodes can create. So what you would do, you would randomly draw edges between these nodes, different amount of edges, etc. And there is a finite solution to this problem. So you have 192 nodes, and then you would draw a lot of different combinations of edges in order to get the sample space. But if you're thinking a bit more about this, you're soon to realize that this finite space is quite large. So only if you're thinking about the network of 17 nodes, you would end up with a directed network sample space that is as large as the atoms in the universe. So you see that this is a crazy amount of different options that the sample space would give us. So this is not possible computationally, and therefore we need to find a different approach, and we need to approximate this stochastic process. And there the proposition is that we use maximum sorted likelihood and Markov chains. And that is a very crucial part of this ERGMs, is exactly this approximation process. And I think also there lies the opportunity for us to improve the model to get it done, or to get the job done faster. So there might be the largest leap of advancement that we might see in future. But the idea of Markov chains, I guess you are aware of. So you start with something, with an observation, and you continue from that. So you always, it's a path. That means that always given the edges that you have, you add another edge, etc. So it's like a random walk to some degree. And that means that already in this approximation, you assimilate this interdependence between nodes. So it's not it's a random process, but it's not independent. And that's a very crucial idea of the ERGM. And then with this approximation that you would have down here in this, so this is the equation that you will see in most inferential network papers where they explain ERGMs. What you would see here is the total sample of possible networks, which is our approximation. And on top here, you would have the observed network. So what the probability of the precise network would then be is the observed parameter that you have here divided by all the potential parameters that you have out there. So how we could think about it is, let's say there is this triangle, which is one of the famous structural terms in the network. So it just means that three nodes are connected. There is a high likelihood that if A is connected to B and B to C, that C and A are connected to. So let's say that our network has particularly a lot of these triangles. So you would count, or you would compare the likelihood of the observed network of this parameter to the distribution across all the possible parameters. And then you could say, is it more significant or is it significantly different from what we would expect in a random network? Is it a very specific thing from our observed network, or is it something that we generally observe too? So, and that's how you get the significance levels and the parameters, the output of your ERGM. So this is the basic idea. And to summarize the idea and how we can think about it is about this duality. So what we have, it's theoretically and methodologically. So we have, theoretically, we must think about individual ties that form randomly, but are somehow constrained by the structure. So And methodologically, this means that an ERGM is a model that models individual tie formation, but is constrained by the structure. So this is this duality. We focus, basically we start from this tie formation, but we have the other stuff in mind. Yeah, so this is the basic idea. And from these ideas, so what an ERGM is, we can move on to what we throw into this model. So we can add 3 things in a model, which is the exciting part of estimating an ERGM. It is, first of all, the node variables. That means these classic variables that we have in all cost section analysis, where we, for instance, look at variation in terms of, I'm always talking about international relations, so sorry about that, I'm slightly biased here, but if we are looking at the nodes, we have, for instance, variation in regime type, variation in trade openness, variation in population, etc. If we're looking at states. At the edge variable, we look at the relationships between nodes. So here we would look at, for instance, trade ties between dyads, or which means the trade network, or we would look at agreements that countries share, etc. So this would be essentially other networks that we can throw into the network analysis. And the last bit, and that's also where we, I think, as a field still struggle a lot, are structural variables. So here it is exciting, of course, because it allows us to have new theories, but I think we still lack a bit in that regard, but I have some more notes on this later on. But structural variables are things like, yeah, we expect that there is a lot of competition going in there, so I might see that there are a lot of these triangular closures, for instance. Or I think that certain actors are very popular rather than others, so I would expect that we have high degrees, so like this. I will show you a figure on this later on, which measures popularity, etc. So these structural terms we can include as well. And I just made 2 quick slides on structural terms, but there are a lot of them. And even if you dig a bit deeper into ERGMs, you can create your own structural terms that are not too complicated. So it's not too complicated to create an own one. You just need to understand the concept of these structural terms. And how we understand these are, we understand them as change statistics. So, and that's also how I tried to explain triadic closure or the triangle. So that means that we look at nodes, and then our measure would be the thing that is added to the nodes or to the situation. So for the very simple parameter or structural thing that we have in a network, it's of course the edges. So that's the very the smallest unit of structural measure that we have. So we start with A and B not being connected, suddenly being connected. And that's how these structural terms are described mathematically also in terms of this change statistic. Reciprocity, for instance, means that A sends a tie to B, and then as a response, B sends a tie to A. And then transitive closure, triangular closure, so there are different terminologies used for this, is A sends a tie to B, B to C, and as a response, A sends a tie to C. And then we have 3 cycles, etc. So these are some network terms, but there are many more, and the documentation of the ERGM is quite nice to get into this. And I also can recommend the Morris et al. Paper, because they talk a bit more about the different specifications of these different terms. Exactly. And then, so these are more the simpler terms, but I want to emphasize one particular parameter that we could include, which is the geometrically weighted triangle, as we could say. So HY shared partners. And there are a lot of these geometrically weighted things possible in an ERGM, but also in all the alternative models that we have in this family. And what it does, it looks not only so local at the structures, but expands the perspective a bit. So it adds, so this would be the classic thing that you have seen in the slide before, A, B, and C, this connection, but these geometrically weighted terms add then more levels. And the more levels it adds, the less weight it gets. So that means that then there is a second triangle connecting A and B, and then there is a third triangle, and so on. And that allows you to get a bit of a bigger perspective. And the consequence of this, if you include these terms, is that sometimes your models fit the data better. So these are quite nice tricks to have in order to make a better estimation. Well, and then if you want to look at the ERGM terms, here is the command that you can call in order to get to know these terms a bit better. One really important thing, which unfortunately is ignored in several papers that are out there on using exponential random graph models, is the model fit. Because if we have a very bad fit of a network model, we can throw it in the garbage essentially. Because if it doesn't fit the data, if the structural terms misbehave to some degree, then we find wrong, we make wrong conclusions of our output. First of all, you might see the situation that your model takes forever converging. This can be either because of you having a big data set or because bad model fit. And therefore, it's really important to look into these graphs that are implemented in all different ERGM models that we have. And what it does, it compares the local structures that we found, that we tried to detect in the model, and compares it to the statistics of the observed model. So how well is the structure reflected in our model? And I will show you later on in R how to do this. Yeah. And then I want to talk about three, or essentially two problems that I faced a lot, especially in the beginning using network analysis, but I think it's a very common scenario that we have, especially for us in political science, where we have networks that are sometimes very sparse. So we have a lot of nodes in there where that are not connected, etc. And then suddenly we face the problem of degeneracy, and that means that the model or the Markov chain walks to an extreme, either of having all nodes connected or having no connections at all, and is stuck there and cannot improve. So what you would have then is that the model doesn't converge and you don't have any results. Some reasons are, this is something that can tell you that this is right now happening. So this is a simple model that I just tried to estimate, and then what I could see is that the iteration process moved from some improvement to more improvement to less improvement to more improvement, etc. So the improvement process was not constant, but rather jumpy. And that means that the algorithm really struggles to find the optimum. First of all, it's slow, and it does not really know where it should land. And one underlying reason for this problem is often that your network terms correlate highly. And that is not so easy to think about, but sometimes we, especially if we're using regression analysis and we go through the review process, we tend to just include all the stupid control variables that the reviewers tell us. But in the network analysis, this can be really problematic, because including more control variables and more structural terms might lead to collinearity. And collinearity is one of the most fundamental problems that we need to avoid using network analysis. So you really need to think carefully, does this term, does, for instance, the degree correlate with the triangle? or do the structural terms to some degree overlap, and do I measure the same? And if this is the case, then we need to drop it. Otherwise, we will have this situation of this extreme walks where we land in a situation where we get stuck. And there, the discussion is quite funny in the literature, because all the ERGM proponents say, well, this is a blessing, actually, this degeneracy. I think it's super annoying because it happens quite often, especially in our sparse networks. But they say, well, it's just because you didn't find a good theory. So if we would have found an appropriate theory, this would not have happened. And that's true, right? We need just to find a very good theory, but that is a very hard thing to do, especially for us being quite new to network analysis. Our discipline has not developed all the concepts that well in terms of network terms. So this can be a quite challenging process until you find a good model that fits the data well. I think it's great in that respect that we really need to think hard about the theory and find good model terms and be much more conscious about model fit. But on the other hand, it is hard work. And the second problem that we have in networks is that it requires a full data set. So we cannot have missing data in there. Why is this the case? This is the case because imagine any structural term, you cannot really measure if there is a missing link. For instance, what would you do in a triangle if you have A, B, but C is missing? The triangle is not present. So that means that missing data is not allowed, and you will not be able to estimate an ERGM throwing in missing data. So you need to think about any imputation method in order to get rid of this missing data points. And there are, as we know from regression analysis, several options. So first of all, you can drop the lines with these observations. So this is the first scenario, and I will tell you shortly what these fields mean here. So only use the available cases. You can also do something like null imputation. So that means that if you have a node where the information is missing, you just add a 0. Otherwise, you could also simply calculate the mean of all the other observations. That's also something we like to do. And then the third option that is the more accurate one, I think we would say in the literature, is using predictions for our missing data. So for instance, the Amelia package in R would allow us to, or the mice package would allow us to fill up the missing data points. And that's actually something very commonly used. And also what network analysts do often is using this mice package, for instance, or Amelia, in order to fill the data. But you might already think that this could be problematic because actually we have network data and suddenly fill it with a method that is regression based. So there is an implementation in one of the ERGM family packages where they use the prediction of a network in order to fill these missing points. And that's these two cases here. So here the simple ERGM, that's the Bayesian approach of an ERGM. They don't use that complicated of network structures, and here the complex one, they use things like this geometrically weighted things in order to fill the data. So here these are predictive models using really the network structure. This is deleting cases where we have missing information, and here we impute with a null. And what you can see here, these things signal the bias, the level of bias. And the darker the field, the higher the bias. It's just green means negative bias and a positive bias, and the purple one a negative bias. So what we essentially look at here is the darker the field or the shade, the more bias we have. And you can see that the bias decreases substantially once we use these predictive models. So since the discipline is so new, many do this, null imputation or mean imputation, and using a regression-free predictive model. But this should suggest that we should more look into this filling up of the data using this complex or this network structure in order to predict the missing data points. So this can be a drawback because we need to think about the imputation, but even in regression analysis, I think you would agree that missing data can be a problem. So with this in mind, and I already mentioned it quite sometimes, is that ERGM is one starting point, but there are many different options to estimate or to deal with different scenarios of data. So you're not stuck with one network being observed at one time stamp or one time point. So you can rather, there are different options that you have. And I just want to give a very brief overview because I think it's nice to have it in mind. And this is also what I will have in the R code then in order for you to, if you need, use the different models. So one development which I think is very promising is dealing with unobserved heterogeneity, because as I said before, there is a substantial problem if you don't have a good theory. But how can we really think about all of the different things so that we don't have a non-equal distribution of our error terms? And therefore, there are several advancements in that direction. So one of the first ones was the so-called ERGM, where they tried to model node heterogeneity. And then just last year, there was a publication even improving this ERGM using a mixed ERGM, where they also take not only node heterogeneity, but take in this node heterogeneity, this structure into consideration. So these are two advancements. The first one is already well implemented in an R package. Another one, which I think is not quite there where we want it to be, are dealing with weighted networks. So ERGMs that I haven't mentioned that yet, but this can also be a drawback. The edges have to be ones and zeros. So this is often a problem for us. What I normally do is I just simply use different thresholds in order to estimate where the significance drops, etc. Because this ERGM, like this weighted ERGMs, they are pretty slow, especially if you have a bit bigger data. And it is also quite hard to find a good starting parameter. So you need to play a very, very long time in order to make this model efficient and good for your case. And if the data gets bigger, it's just super slow. So yeah, I think the right now more practical option is to use different thresholds. So this would be a weighted network. Again, this is from my dissertation where the different edges show the degree of cooperation between different actors. Then another one which I find quite nice is the so-called ERGM, and it's a model using the Bayesian approach in order to update the beliefs of the network structures, and it does that continuously in this Markov chain, which then ends up in a much faster convergence. And even though if you start off with a degenerative model, so with a model that is not quite good in terms of theory, this can converge and can bring you to some results. And from there you can then move back and improve your results. Because just the information that it doesn't converge doesn't tell you yet where the model fit is bad. But if you at least can converge, I think we can improve the model much, much better and faster with this ERGM. And the last one, which I think is very relevant for many of you probably, because with more data and survey data, etc., we often have time variant data, dynamic data, and there is a so-called ERGM which is also implemented in a package, and it's not that slow, so it's okay, which can estimate these dynamic models. But here it is important to say that there is a competing algorithm that is not that different in terms of results, but has some different assumptions, which is the stochastic actor-oriented model. So this is somehow the competing part of the ERGM family. But I think they also have really nice features. It just has a bit different assumptions. And if you're using a dynamic model, it's definitely worthwhile also looking into this. Okay. And then the last ones that I will mention is, I talked about egocentric networks in the beginning. And here you could estimate a TNAM, that's an autoregressive model where you have the node as a dependent variable, and then you use the networks to explain the characteristics of the node. So that can be quite nice too. And then there's also an event model for network models. So these are kind of the current options that we have. I think it's a fast developing field, so we will expect many more there coming soon. Okay. And now I will quickly move to R and show you what options we have, or what the different scenarios that I just showed you, how we could implement this and how we could generate actually a network data from a simple static data set that we normally have. So let me share R. So I can share the script if you're interested, of course. But what I have here is just a collection of packages that I need, or this is actually just for laziness. But here we have ERGM, which is the classic package where we can estimate the classic model, then BERGM for the Bayesian model, and BTERGM for the temporal model. And also something that I would like to mention is the visualization of networks, because once you want to publish something on networks, it's always nice to have at least one of these fancy graphs in there. And there are different options, and I really like the ggplot2 functions or gallery, so that's why I use the ggnet, which is built upon this, so I can work with the library that I already know. But there are other options that I mentioned further down. For instance, iGraph, network P3, and visualization network are other options that you have. There are many more, but here you can really do whatever suits you best. So this is a data set from trade agreements that we have online. Can download this here, and then I just prepare it so that we have dyadic data. So what you have here is the graph that I've shown you in the right in the beginning, the relationship between countries. So one dyad is a dyad between two countries. Okay, so that's what I've done here. But the interesting part is that's where you mostly start from, right? You have a dyadic data set, and then you want to do something with this in terms of networks. So what you want to do at the beginning is create a network, right? So what I mostly do is simply filling up a matrix with the information that I have in the dyadic data set. So you would identify the units that you have in there, and then draw a matrix with the equal rows and column length in terms of how many units you have, and fill everything with a 0. So this is just an empty matrix with the amount of units that you have. And then you slowly fill this with a loop. We have also, in one of our papers, we wrote a little code, and my co-author published a little package so that this process can be done quicker, especially in terms of temporal networks. Okay, then I fill this up. And then the important part here is you transform this matrix to a network. So you have a matrix, an adjacency matrix, where you always say this node is connected with that one or not. And then you make this to a network, and here you can tell whether it's a directed network or whether it's undirected. And in that case, it's just a joint agreement, so it's undirected. So I put this to false. Okay. And then we can plot this network with the ggnet function. And here it's basically, if you use ggplot too, it's basically the same logic. So this would be the network that you have seen in the beginning. This is just an information how to plot. I think what's more interesting for you probably is the estimation process. So we have not, unfortunately, we don't have time to, of course, go through all of the different options. So I selected the 3 most common ones, and where I think we all start with ERGMs, TERGMs, and the Bayesian approach. And I simply generate a random network here. So using the same idea that I had above. So here now we have a network, a random network. And the important thing for you then would be how do I add the information that I have in addition, like the node attributes, etc. And here we can use the function called set vertex attributes in order to add additional information. Exactly. So now we added 2 variables, x and z, that are in my data set, and I want to say whether this these are node attributes. And then I talked you through these ERGM terms, but that's something for you to explore because it depends on your theory. And the null model, which we have in the regression analysis, is simply a model where we only have the edge term in there. That simply looks at how dense the network is. Alternatively, we also could put density in there, but edges just counts how many edges are in there. Okay, and so I estimate the null model. Essentially, the function is quite simple, trivial. So you have the ERGM as the model, net as the dependent variable, as the dependent network, and then you have the structural terms, the node terms, the other networks, etc. on the right side. So this would be the model. Yeah, of course, not significant, it's just randomly generated. We can also check how many triangles we have in this network. So we have 2,743, and then we could include this measure in the model. So here I have 1 or 2 structural terms, the edges and the triangles. And in addition, I control for the node variation, so for variation in terms of the x variable. And that would give me a model that takes a bit, not too long, hopefully. First, I wanted to make an illustrative example with real data, but it takes too long. So that's why I chose this randomly generated data. Okay. So the output then tells us, well, it's not abnormal in terms of edges compared to random networks. It seems to have a bit less triangles, but it's also not significant. And the X covariate is also not significant. The important thing then would be to look at the diagnosis. So look at how was this approximation process going for the program, and that you can do in that respect. And what you have to look at here is whether all your terms here look like a normal distribution. And if that is the case, that's great. If not, if they look a bit weird, you need to reconsider this particular term and maybe drop it from your model, and then you can improve your model. So this would be a first way to advance the model in terms of statistics. And the second thing that we want to do is plot this goodness of fit measures that I've shown you on the slide. And here you can see this figure that is very similar to what you have seen in the slide, and what you look at, whether this black line overlaps with the box plots. So if there is a bad fit, the shapes go somewhere completely different, and then you have a bad fit for your data. So this would be the last step in an ERGM. And the other parts are faster to explain. because essentially it's just another function. So ERGM can be, especially for larger networks, faster. For smaller, it doesn't matter and it's not faster. But this ERGM package, so this Bayesian approach, has this nice function of dealing with missing data. And that's what I mentioned here. So if you have dealing with missing data, then the ERGM M is something you can estimate in order to fill up the missing holes. So we can estimate this. It takes a bit, but it's this updating process of the network information which it does continuously. Yeah. And this model is something I think a bit underused in the literature, but has many, many advantages. And we can again plot this convergence process, and here we can see we kind of have this normal shape, but there seems to be some anomalies. So we have to probably reconsider whether we want to have these things in there or not. And then again, the goodness of fit measure, which is also implemented in the package. This always takes a while because it needs to compare the real data with the network data. Yeah. So also here, it seems that we have not such a bad fit. And then the last thing, and that's the temporal, the dynamic model, is where you can use this package, the code that we used in one of our papers, where we use ERGMs. And just to reshape the ERGM very quickly, Vincent Arabandek, a co-author, published on GitHub this spatial helper. So you can create spatial legs in order to make it easily comparable to your network model, and you can fast and easily create networks without really dealing with a lot of loops, etc. So I'm using this package, so it's well explained on the homepage there. The only thing I need to do in order to convert the panel data to network is then call the function panel to network, and it does the magic. It then puts everything into an environment, and in there we still need to define what our dependent network is in order to let R know where it should start the estimation from. And same as for ERGMs, you can look at ERGMs terms, which are essentially the same. But one exciting thing about these dynamic models is that you can use so-called memory terms that allow you to model the dependencies, the autocorrelation essentially. So it allows you to model, for instance, here, the stability of the model, whether the tie that was existent in t-2 is also existent in t-1, for instance. Yeah. So this would then be the model that we estimate, is essentially the same logic, but we have some more options in there. Yeah. And then below is again the model fit, which again takes a bit. But so this is a very quick quick guide through the most common terms that you can get started with. And I also link on all the slides additional package to the other functions that we can see further down. So again, here a very similar result. It seems that the fit is quite okay. So yeah, if you want, I can share this very trivial, simple code. But I think the spatial helper thing is something that facilitates at least the generation of the network. And otherwise, it's simply an edge. Start with the matrix, and then you can do everything from there. Okay, so I'm gonna move to the slides again. And I promise I will not talk too long anymore for the questions. But if you have questions coming up, simply drop them so that we can yeah, recalibrate our time. the thing with what I want to end the discussion and the talk are some current challenges that I think are out there and that could also motivate us to move our field a bit further using network analysis. So the first thing when I look at network analysis in political science is I think a bit about this figure, what you can see here. So on the left side, I would imagine all the network terms that we have, for instance, triangle, in-degree, etc. And then we have our political science terms, power, competition, diffusion, etc. And somehow I think that this link between the network structures and the terms that we have out there is missing. So I think what is really necessary is for us to agree on how can we measure diffusion, for instance. What is an efficient network statistics in order to really measure this political science concept? For sociology, it seems to be quite straightforward. So there are much more network papers out there because it seems that their concepts really fit network structures immediately. But we sometimes lack a bit thinking about the relationships between our actors. And this might be a cause why we are not yet able to really link or agree on network terms. So often what I see are network papers where you have power measured with one network statistics and then power measured with a completely different network statistics. So I think there must be agreement to somehow, that we must find agreement on which concepts measure or are illustrated by what network term. So this is a task that is ahead of us in the next years, I guess, in order to really make interesting papers. Because like this, it's more like, oh, I'm selling a paper, having a fancy network model, but the theory is kind of only understandable to network geeks or to a very small community, and the others think, oh, it's just cool because it's fancy. But I think there must be a more substantial discussion on linking theory and concepts. And the second thing is the methodologically challenging part, namely using bigger networks. I'm not even talking about big networks, but just a bit bigger networks. So I just mentioned the project with Vincent, where we model the convergence or the diffusion of text 3D design. So we're using text analysis in order to look at how similar does this text 3Ds get over time. Essentially, we have all countries in the data set and 74 time steps. And we combine this with text analysis, where you also have to have different, different pre-processing steps, and that makes you very likely that you have many models because you need to test a lot of robustness things. So essentially what we had 64 estimations per model and these time steps. What we ended up with was this process. So we rented a very expensive cloud computer, or cloud, we rented Amazon Cloud. It took us ages until this was done, weeks essentially. So in this time you couldn't do anything on the paper, so you moved on to other papers. Computing was done, both of us were stuck with other papers. We slowly got back and estimate again and wait. So essentially what we had was a very, very inefficient research process for our paper. So this was super frustrating because I think the paper itself was exciting and I was motivated to do it, but just the process of developing it was so annoying, and it took us years to really finish this final draft that we seem to have now. But yeah, it just takes forever. So there are even bigger networks. Another project that I have where I found it a bit frustrating is we have all constitutional court decisions from all European countries scraped, and one country produces 4,000 of these decisions per year, and we wanted to show the links between these decisions across all European courts. So that would be a huge network, and it's impossible. So we need to think about alternative solutions. And if you're looking at, I guess you have a lot of survey data, text data, panel data, you all have this situation with a lot of data points and a lot of nodes. So what can we do, or what are the challenges? First of all, the challenge is to load this data, to load these big networks, because these are all matrices, they need a lot of space in in the memory, so it just takes forever. Then it struggles to process the Markov chain because it's so long, because it's such a big data. And the third thing is, if you remember at the beginning, this Markov chain assumes that given the knowledge that you have from network, you estimate the further tie. That means that we assume that the individual tie knows a bit more about the structure that we have. So this was this duality that we had. But is this really realistic? If you think about a big network, is it realistic that we think that the formation of a tie or the tie knows about all the other structures of this big network? So I think this is an assumption that we are no longer able to hold. So what can we do? We can rent a computer. It's expensive and annoying. And we can model a full network, but improve our model. And we can use structural reduction. So let me talk you through the modeling of a complete network. So there are different options. The first one is you still use your regression analysis, but you accept that you don't really control for these endogenous terms, but you rather compute them artificially. And there is a nice package doing this. But then you accept that there's somehow a misfit in your model. The other thing is you improve your estimation. And here you can use, or you can do something with the isolates, so ignore the isolates or something like this in order to improve it. You can do parallelization. You can do a pseudo maximum likelihood estimation, but that has been shown to be less accurate in terms of estimations. There are a lot of, there are big confidence intervals and it's less accurate. And then you can have a graph limit maximum likelihood estimation where you do grid search in order to randomly estimate the parameters in your model, and you do then the grid search of the optimal parameters. But that is problematic for our networks essentially, because our networks are sparse and there you need dense and symmetric networks. And the final thing, so this, we'll skip this in respect of time. The final thing is, I think, where we are stuck now a bit, are the structural reductions of networks. So what we can do is we can think about aggregating the nodes to groups. So for instance, for our case of the court decisions, we could aggregate the court decisions to timestamps of the court. So instead of having the individual texts, we could have the courts as a node, and then it would be reduced dramatically. What we can also do, we can also only look at the core of the network, so only the center of the network be estimated and forget about the rest. And finally, we can do some network or some meta network analysis, which is, I think, really a cool idea. So what you do, you estimate subnetworks and then use this information from the subnetworks in order to model the bigger network. So you can combine these different levels with different structures and different information. And that allows you to parallelize really efficiently and to make the conclusion in such a way that you also accept the dependence assumption. So now I rushed through a bit the last bit, but let me conclude. So first of all, I think there are 3 messages that I want to contribute to. So the first one is that we can be optimistic. I think there are a lot of people out there working on the methods and that try to match up our requirements, but there are still some things that we haven't dealt with. For instance, there is no efficient 2-step network model. So what do we do with selection bias, endogeneity, etc.? But there are methods that try to catch up with this requirement. The second thing is that it is really important to think about networks not only as this fancy methodological advancement, but more of an opportunity to advance theoretically. And only if we move forward theoretically can we have the nice substantial papers, I think, that are relevant for a broader community. Because I think it's a bit passé that the network models are the most fancy thing out there and that we can simply publish it because we have network models. So we need to be more substantial and thoughtful about the theory here. And then the third thing is that big data is amazing, and we all have access to much more data using scraping, etc. But there are a lot of challenges for us, but I think we just need to be a bit more flexible about how we think about the data, how we calibrate it. And this meta network analysis, I think, is one of the most promising parts of moving forward here. I think there are improvements in the estimation strategy, but the time improvements are not so big. So yeah, we need to move forward in terms of rethinking it, but then also rethinking a bit more the approximation algorithm if we are more tech averse or more tech fun. So that would be the talk from my side, and now I'm looking forward to questions.
So thank you, everyone. If anyone has any question, feel free to ask. I just got one, but I have to read that first before I can ask it. Okay, no, that was just a note. So I do have actually like one just understanding question, if you want to call it like that. So when we talk about computational power, what would you understand as a large network, and what would you understand as a small network, and when does it start to become complicated when it comes to computational power?
So a large network is really, it depends, right? But it's more how complicated the network is. So how sparse is the network? If you have, for instance, a network of only 200 nodes, but it's very sparse, then it could be considered as large already. But if you have a quite informative network and you have maybe 500 nodes, then it can still be okay, probably. So 1,000 nodes, I guess we would say it's big, but then it gets into the millions, of course, if you're looking at user information on social networks, etc. So this, of course, is big. But we already get into these problems using only 200 nodes if we have sparse data. And also, it gets very big if we have timestamps. So if we have dynamic data, then it's soon very big, because then we have one matrix for each timestamp.
Yeah, sure, that makes sense. Oh, I think there's another one. So yeah, could you maybe explain again what the main difference is?
So the major difference is really the assumption of how you think about the change statistics. So the ERGM looks at actors' change statistics. So the ties change so they look at the tie change. So once a tie is added, how does it change the statistics? The alternative approach, the stochastic one, is more that it looks at one timestamp and then at the aggregate network. So how does the full network change from one timestamp to the other? And the ERGM group sells their approach as an advantage in terms of having smaller timestamps. But actually the other group says that's irrelevant, and I think they are right, because we have these timestamps anyway. So we look at these changes anyway. So this is the assumption, and there are really minor differences in terms of results. It depends on the structure of on the dynamic structure. So what are the timestamps and when do the changes appear? Are they more sudden or are they incremental? If they are incremental, I would suggest more this ERGM, and if they are more like a group change, then the other model seems more appropriate. Both groups have published papers selling theirs as being the better one. So I think if you really want to dig more into this, reading both papers on this is quite helpful. Yeah, I think that I tested on my data both, and the results were really similar. But this is only my experience. So also their simulations, they were not so different. I mean, they are then nitty-gritty on some of the the goodness of fit measures. Yeah.
Okay, cool. I hope that answered the question, but it looks like that. Good.
Okay.
Okay. If there's no other question, I do have another one. It's like in one of the very last slides, you mentioned that one way is either to aggregate nodes or to model only the core of the network. And I was wondering, what are the costs if you do that?
Mm-hmm. Yeah, I think it's more a theoretical question, right? I mean, aggregate is quite, like for my example, for instance, because we are facing this discussion right now in our project where we scraped all this data for all the years. It took us half a year to scrape this stuff. So we were really proud of having the data, and now suddenly, it's too slow. We are not able to estimate. I mean, we knew it before, but we still wanted to have the data. So aggregating it to cohorts is quite painful because we lose so much information, and there's so much variation between topics that are, etc., that is only the information at the text level. So what I think is then a workaround here would be this meta-analysis, where we estimate networks for individual cohorts separately, and then use this information as node information than estimating the bigger network. So we essentially just split up the task in different sections. And then I think we can again work a bit around. Looking only at the core of the network, honestly, this has been proposed in the literature, but I have never seen a paper using this. So I guess there are high costs for this, ignoring isolates, and because I think that the structure is wrong to some degree. So I could not really think about a situation where this would be really helpful, but might be in some situation. Yeah.
Thank you. Okay, I think there's another question. If you want me, I can, yeah. I
can read it. So is it important if nodes are fundamentally different? Of states and real nodes. Yeah, I mean, I think it's just the homogeneity. Like, if the nodes, I'm not sure whether you mean that you would have both in one network or not. Like in my example of trade agreements, they are aggregated indeed. The stuff like if you have the EU agreement, for instance, and the EU negotiating an agreement with another country, then I aggregated it, but you would have Bahrain, for instance, on the other side being a country. So these are different structures, yes, indeed, and that's why I used, like in a regression analysis, different variables to control for this heterogeneity. And then another thing, what you could do is you could, if you don't know about the difference in the structure, you could look at this options, this ERGM, mixed ERGMs, etc. But I think we can control. It's a similar thing as in regressions. So the difference is in nodes. It's not that different. Yeah. Cool. Thanks for the question.
And I think there's probably, I don't know, probably the last one, but there's another. Yeah, okay, apparently it helped. Yeah. So there's another question from Dennis who asked which are the most promising but still underexplored areas for using network analysis?
Yeah. I think, I mean, again, I'm a bit biased, but I think in general, they're combining text with networks is something really nice, where we have in most fields a lot of text data and then looking at the relationships between them. I think that that's something that we can do in most fields, but I think there are a lot, like I have one colleague of gender studies, and I think she could do really exciting things with networks, because there is this collaboration across countries, etc. But I cannot answer it very well educated, because I'm working in IPE IR, But method-wise, I think like combining different data sources with networks is something that where we can advance the stuff. And also survey data. I mean, there is such great data out there, and it's also sometimes relational, but this is underexplored, I think.
I think there's another, like it's more of a side note, that there's, I just need to read it first.
I read the paper. I think it's, again, this sparsity issue, but I need to read it again. But I read it on the weekend, and it was, even though it was sparse, I think for a social network, it still needs to be symmetric, I think. But I need to go into this again. So it can be sparse, but the structure in the sparsity part needs to be at least similar. But I think that goes in the direction that I have shown, like improve the, so it does the weights of the isolates, it puts down so that it does not draw these isolates at all the imputation methods, but rather tries to ignore them a bit. I think it was one of these approach, like dealing with isolates in a different way. But there is no package yet. So,
not yet.
Implemented ourselves.
Okay. If there are no more questions, I think we're done. Thank you so much for this really nice and neat overview, Lisa. That was great.
Thanks for the participation. It was great.
So thanks everyone for showing up today and joining our talk. It was a pleasure having you here.
Thank you. Enjoy your day.